Okay, so for this, it's a great pleasure for the second half of today's symposium to have Aasmund Folkestad here from MIT. And he's going to talk to us about his work with Netta on the canonical purification of black holes. Take it away.
Okay, thank you for the invitation to speak. So yeah, I'm going to tell you about the canonical purification of evaporating black holes based on work published earlier this year with Netta. So let's just jump right in. So a major goal of ADS-CFT is to extract the gravitational picture directly from the CFT quantum state. And kind of two slogans that captures a lot of what we know about this problem is the slogan of entanglement builds spacetime and ER equals EPR. So this talk will think about these slogans, what we know, what are subtle aspects of them, and try to clarify some interesting aspects of these slogans. And of course, the kind of canonical example of entanglement building spacetime, or ER equals EPR, is the ADS-Schwarzschild black hole and its relation to the thermophile double. So on the left, I drew the ADS-Schwarzschild black hole, and we know very well that this is dual to the thermophile double state, which is given by this sum where ket E is basically the energy eigenstates of one of the CFTs. And here you take a tensor product of the two CFTs that live on each side of this Penrose diagram here, and you take some sum. And the interesting thing is that to the extent that each of these states, these energy eigenstates, have a geometric dual, let's assume they have, then essentially the geometry dual to the tensor product is just some disconnected geometry, two identical spacetimes that are disconnected. But somehow when you sum over them in this way, you actually get a connected spacetime. So summing over disconnected spacetimes seems to lead to a connected spacetime, which is interesting. And of course, when you form this sum, you introduce entanglement in your state between the two CFTs. So somehow, we see that the connected spacetime emerges from entanglement, or a wormhole. And more generally, in ADS-CFT, we know via the QES formula that a wormhole always implies entanglement. So we're going to talk a lot more about the QES formula, but if you just try to evaluate it in any wormhole spacetime, you will see that the entanglement between the two CFTs will be non-zero. But an interesting question is, when can we flip the arrow? If we have an entanglement, do we have a wormhole? How can we tell? And we expect that there has to be some situations where we can flip the arrow, because the slogan isn't ER implies EPR. So let's try to think a little bit more precisely about this. So consider some CFT quantum states on some tensor product Hilbert space of, say, two CFTs, HA times HB. And let me make a proposal for what it could mean that wormholes arises from entanglement. Okay, the slogan for this proposal is going to be that semi-classical, highly entangled states are always wormholes. Okay, so consider this proposal. Assume that the state psi has an order 1/g Newton amount of entanglement between A and B. And psi, we also know that it has a semi-classical dual. Then the semi-classical dual is connected. That kind of seems like a reasonable conjecture to have. And in the classical limits, it is true. But we're going to show in this talk that this is actually false. Once you include quantum corrections in the bulk or work to subleading order in 1/n, this is no longer true anymore. So let's maybe make a different proposal, which I'm going to give the name ER equals EPR. Assume again that psi has an order 1/g Newton entanglement between A and B. Then there exists a factorized unitary, UA times UB, such that the resulting state has a connected semi-classical dual. So why do I call this proposal ER equals EPR? Well, let me read a quote from Aldacena and Susskind's original paper. They write that, and this is in the context of an evaporating black hole, and they talk about the Hawking radiation. So they write, if an observer collects the radiation, then with a powerful enough quantum computer, she could collapse it into a second black hole, which is perfectly entangled with the first. In addition, by operations solely on her side, she can put the pair of black holes in the special state that produces the smooth ER bridge. So we will show generally that this quote is true after the page time, but it actually needs refinement before the page time. And kind of the key thing that's not entirely correct is this thing here in black, which is solely on her side. But this proposal 2 has kind of taken into account that this modification is needed by allowing non-trivial UA and UB, but we'll return to this. Okay, so our paper and this talk, in our paper and in this talk, we construct a general procedure to realize ER equals CPR after the page time in evaporating ADS black holes. We show that a highly entangled bipartite CFT state with a semi-classical dual need not be a wormhole. We argue that the reliable CFT diagnostic of spacetime connectivity is lacking. And here are some other notable works that think about ER equals CPR in the context of evaporating black holes and the novel developments from 2019. Okay, so let's assemble the toolkit that we need to reach these conclusions. So the first one is of course, the QAS formula, which we're going to use all the time, and probably most of you know. So basically, it says that if you have some subregion A on a time slice in your conformal field theory, and you want to compute the von Neumann entropy of the reduced state on that region, then that's equal to the generalized entropy of a certain surface XA in the bulk, the quantum extreme surface, given by taking the area of that surface and including the entropy of the bulk quantum fields in the region between XA and A here. And yeah, as I said, XA is a quantum extremal surface, and it's a stationary point of this functional here, Sgen, on the right-hand side. And this XA is, of course, anchored at the boundary of A, like I've drawn it here. And the entanglement wedge of A is essentially everything between A and XA that's space-like to both. Or more precisely, it's the domain of dependence of some Cauchy slice that has XA union A as a boundary. And everything in that domain of dependence, everything in the entanglement wedge is encoded in the state rho of A. Good, so that's the first tool we'll need. The second tool we'll need is the canonical purification. So the canonical purification is a special map of a mixed state on some Hilbert space H to a pure state on the Hilbert space H times H, so the doubled Hilbert space. And if we just diagonalize the density matrix, it's very easy to write down this map. So you can always write density matrix on this form here. And essentially, you obtain the canonical purification by just flipping the bra hair to a cat. I also actually added a star here because in quantum field theory, you'd actually like to also apply a CPT conjugation on one of these states. But that's a detail that doesn't really matter much to our story. But that's how it's done. And just the basic example, if you take rho beta, so just the thermal state, and you construct the canonical purification, then you get the thermophile double. And the great thing is that the bulk dual to this procedure is well known at this point. So given a mixed state rho on a complete boundary time slice, the dual to the canonical purification, square root of rho, is given by gluing the entanglement wedge to a CPT conjugated copy of itself. So let's just draw this whole process in pictures so it's clear. You start with some state rho and its entanglement wedge like this. And then you glue it to a conjugated copy of itself. And you see that this second wedge is kind of flipped on its head because the CPT involves a time reversal. And then finally, to get the complete spacetime, you just evolve forwards and backwards in time. And then you get this spacetime here on the right that's dual to, well, this should be a cat around the square root of rho, but to the canonical purification. And you see I've drawn some red lines here. So in general, carrying out this procedure, you will incur some shocks because this quantum extremal surface, it doesn't have mean curvature 0. So in general, when you do this gluing, you get some discontinuous first derivatives of the metric. So you'll produce some shock waves, and they might even have a negative null energy. But even if they had, we can look at this picture, and it's actually not necessarily a problem. We know that quantum fields can have negative null energy, but you would like the average null energy condition to be true. But in this spacetime here, for example, it's not going to be a problem because you can't draw a single complete null geodesic. So there is no complete null geodesic to even test the ANIC on. So it's trivially true. Okay, good. So now we essentially have the tools and we're ready to move on. But are there any questions on this procedure before I go to the evaporating black hole? Okay, so then I'll move on. So let's canonically purify some evaporating black holes. So let me just summarize the basic features of the evaporating black hole. Of course, these results were found by this great papers from 2019. So if you take say a one-sided black hole that forms from collapse, and then after some time, you turn on transparent boundary conditions on the boundary of ABS, and then you dump the whole, then you allow the modes to escape and go into some reservoir, then you can allow the black hole to evaporate. And we'll take care of the reservoir to be, say, some non-gravitational system. And then before the page time, say if, you take a boundary time slice early, say here, shortly after you turn on the coupling, then the QS is just empty. And a Cauchy slice of the entanglement wedge is just a slice like the black one I've drawn here. Later on, of course, this famous island QS appears. So now if we want to compute the entanglement entropy of some later time slice up here, that's after a page time, then this is the dominant QES, and a Cauchy slice of the entanglement wedge is now like this blue one I've drawn here. That's essentially everything I'm going to need from this story. And just an important thing is that the appearance of this island QS is as a generic phenomenon and not like specific to the specific models or scenarios that were studied by these authors. And just to introduce some notation here. So in the boundary or microscopic picture, I will use capital letters essentially to refer to the density matrices that we have. So in the CFT, I will call the state rho capital BH. And on the reservoir where the radiation escapes, I will call the state rho capital rad. And in the bulk, of course, we know that this blue diamond with the rho BH in non-capitals, that's dual to the blue circle here on the left. And the union of these orange regions on the right is dual to the orange region on the left. Okay, so let's canonically purify now after a page time. So we start with our state. We trace out the radiation. So rho BH is now just dual to this small portion of spacetime here. We canonically purify, which means, gluing this Cauchy slice to a CPT conjugate copy of itself and evolving forward and backwards in time. And we get this Lorentzian wormhole here. Here we also chose to evolve with reflecting boundary conditions, but our story doesn't really depend on what boundary conditions you choose, but it's kind of conceptually simplest to choose reflecting boundary conditions. Good, so we see we get a wormhole. And now comes a key observation. So for a moment, just think about two generic quantum systems, B and R. And let phi of BR and psi of BR be any two purifications of some state rho B. Then these two states are related by a unitary that has support only on R. So what does that mean for the purification procedure I just wrote down? Well, that means that there exists a unitary which has support only on the radiation, which converts this picture here into that picture. But that's exactly the statement of the quote I read earlier by Maldacena and Susskind. So it essentially says that you can act purely on the radiation and convert entanglement into a semi-classical wormhole. So there indeed exists a URAD that converts entanglement between the late-time Hawking radiation and the black hole into a semi-classical ERB. So this is a general realization of ER equals EPR after page time. And another nice application is that of this construction is that it allows the computation of the radiation entropy using the standard QES formula rather than the island formula. So why is that? So if you just compute the von Neumann entropy over rho rad, and then you conjugate with this unitary URAD that is here, then of course we know the von Neumann entropy is unitarily invariant. So then we get the von Neumann entropy of the state here on the BH tilde system, but that's just the generalized entropy of chi. So we computed this entropy without having to like modify the homology constraint or anything like that that appears in the island formula. So that's a nice application. And we could do the same to compute any other unitary invariant, like the Renyi entropies or something like that. And we did this procedure explicitly in JT gravity just to check that kind of we get sensible answers, and we get this space-time I've drawn here. So chi is the QES, and then I've drawn two shocks emitted here through chi, which was the shocks I talked about earlier that comes from the gluing. So here, essentially, in JT gravity, this comes from not the discontinuity in the derivative of the metric, but discontinuity in the first derivative of the dilaton. But you can work out the junction conditions in JT gravity as well, and the analog story carries through. And then you have some additional shocks that comes from the fact that we use reflecting boundary conditions. So, you know, the state we started with had absorbing boundary conditions, but then we want to reflect with, evolve with reflecting boundary conditions. We have to turn on just quickly reflecting boundary conditions on both sides, and that causes some shocks to enter the bulk here. And all the red shocks have positive null energy, and the blue shock has negative null energy. But the ANAC is preserved. Actually, it looks kind of nonsensical of me to say that here, because as you'll see, I've kind of terminated space-time on these lines here. So where are the complete null geodesics to test the ANAC on? Well, 2D gravity is a little bit special in that the metric here is just pure ADS, and I can consider the quantum, I can just look at the quantum state of the quantum fields that live in the bulk and kind of forget about the dilaton and forget, I mean, gravity and holography and whatever, and just study these regions I cut out here and look at the stress tensor of the quantum fields. And you will see that if you trace a complete null geodesic like this up here, the ANAC is satisfied. So that's just an extra consistency check. Okay, so crucial to this whole story is that the Cauchy slices of the entanglement wedge of the black hole were incomplete. You know, they had a proper boundary on the island QES. So let's see what happens before the page time. Again, we start out with the original state on the black hole and radiation. Now, you know, a Cauchy slice of the entanglement wedge is complete like this. Trace out the radiation. We get rid of this system here. Canonically purify. And now that means just like introducing a second copy of this Cauchy slice and evolving forward and backward in time. Should be a cat symbol here again. And, you know, because gluing across the empty set is just no gluing at all. So now we have actually a disconnected spacetime. So there's a qualitative difference carrying this procedure out before and after page time. So an interesting application of this is, let's say we act with some unitary on the BH tilde subsystem, the system that's unitarily related to the radiation, that sends in some signal into the bulk. We see that this geometry, this setups nicely geometrizes the fact that unitaries on the radiation can affect the infalling observer only after page time. So essentially, if you act with this unitary here that I've written down here, if you act with that on the radiation, then you can send some signal in that modifies the future experience of an infalling observer from the BH subsystem. But okay, more interestingly, well, yeah, perhaps more interestingly, what does all of this mean for ER equals EPR? So we now have this scenario. So that's interesting. Collapsing the radiation into a black hole does not always lead to an ERP, even when there is a semi-classical dual. So this intuition from the quote earlier was good after page time, but it's not entirely accurate before. Now, there could still exist a unitary which has support on both systems, such that we convert this disconnected geometry into a connected geometry. I mean, we haven't proven that you can't do that. That might very well be. And equivalently, we can go back and forth with these pictures by acting just on the radiation. So that means that there also exists such a factor as unitary on the regional state that can, you know, let us build a semi-classical wormhole. But it is crucial that VBH is not equal to the identity. This cannot be true if VBH is equal to the identity. And that's because if we don't act on the BH subsystem, then the entanglement wedge of BH, which is just this whole thing, is unchanged. So it just continues having complete Cauchy slices. But then you cannot connect a wormhole into it. The Cauchy slice is complete. It's impossible to glue anything to something that's complete. So to realize ER equals EPR with a semi-classical wormhole before the page time, we are forced to modify the original black hole as well. Acting purely on the radiation will not work. Another thing worth noticing is that derivations of ER equals EPR using the geodesic approximation only works in the strictly classical limit, and they give the wrong result with quantum corrections. So often you see something like, well, the 2-point function of some operator OA and operator OB on the two sides, it's like heavy scalar primaries or something. It's the exponential of the geodesic distance between the two sides with some prefactor m. And then if there is some correlation, then L has to be less than infinity. So, you know, there is some geodesic threading, some potential wormhole, and you actually have a wormhole. But this does not survive quantum corrections in the bulk. So we shouldn't really trust those outside the strictly classical limit, those kinds of reasoning. Now let's look at the puzzle we get from these purifications. So let's look at the page curve, and let's choose the time T1 and T2 before and after page time respectively, and let's choose it so that, you know, the states, the radiation states, have the same entropy, or the black hole state, whatever, assuming unitary evaporation, of course. And now we form the canonical purifications, which are dual to disconnected and connected spacetimes, as I've said now several times. We see this interesting thing that, these states have the same amount of entanglement between the two sides, but one bulk dual is connected and the other is not. So the amount of entanglement isn't a good diagnostic of whether we have a wormhole or not. And let's look a little bit closer at what kind of works, what you can do to diagnose connectivity classically, so we can see what fails when we include corrections. So classically, it is true that if the mutual information between A and B is order 1 of Gn, then AB has a connected entanglement wedge. This is very easy to prove. So if you just use the HRT formula, which is valued at the leading order, then the mutual information is just the area of XA plus area of XB minus the area of XAB, where now XAB is the RT surface of the union of A and B. So you can just draw it in pictures like this. And of course, if this is non-zero, then we know that XA union XB is different from XAB, okay? And that means that now the entanglement wedge has connected when we took the union. And it has to connect. You might try to complain that, well, maybe just somehow now XA, that XAB should instead be the union of this XA prime and XB prime that I've drawn. But that cannot be the case. They really have to connect up, because otherwise XA prime and XB prime would have been the real RT surfaces here, and there's red surfaces would have been irrelevant. But now we've just shown explicitly this doesn't work semi-classically, because in our setups we had bipartite pure states. So the mutual information is just proportional to the entropy itself, which is equal to the radiation entropy, and we picked points on the page curve so that these two are the same. So the mutual information between two sides are the same. So maybe we should try to look for some other diagnostic that maybe can tell us whether we'll get the connected spacetime or not. So one thing that people might suggest is that maybe you can look at this quantity delta S, which is the thermal entropy minus the phenomenon entropy. So essentially, how far from mixed are you? So before the page time, this is non-zero, and the earlier you are, the greater this difference is. And then after page time, it's approximately 0, almost by definition of the page time. So maybe we need small delta S in order to have connectivity. That cannot be the case either, because we can throw pure matter into an all black hole to increase the thermal entropy, but the phenomenon entropy is unchanged because it's the pure matter we throw in. And the QAS will remain non-empty, so connectivity of the canonical purification will remain. We can see this as follows. So the phenomenon entropy of rho of the black hole with some extra pure matter is the same as the phenomenon entropy of the black hole before we throw in the matter. And that's, we know after page time it's less than a generalized entropy of the empty set. So the empty set cannot suddenly become the dominant QAS in this situation. So delta S cannot be a good diagnostic. How about complexity? So before the page time, the canonical purification looks something like that. We have some non-minimal quantum extremal surfaces behind the horizons like this. And we know that these regions in red are exponentially hard to reconstruct using this Python's lunch proposal. While in the canonical purification after page time, there is no such non-minimal QAS in our state. So maybe complexity is the diagnostic. But unfortunately, it cannot be either. When I say complexity, I mean like whether there are geometric regions in the bulk that are exponentially hard to reconstruct. But yeah, we can easily construct a 3-boundary wormhole like this. And then if you consider, say, the time slice, the boundary region to just be the union of the boundary time slices out here at scry1, scry2, and scry3. Then the union of sigma 1, sigma 2, and sigma 3. That's a non-minimal QES. This region in the center here is exponentially hard to construct, but we're still connected, unlike the case here. So complexity doesn't seem to be the answer either. So then what determines connectivity? We can construct two states with semi-classical tools with the same amount of bipartite entanglement, complexity, degree of mixedness, also mutual information, but they have different connectivity. I don't know. We can also write down another interesting example that maybe can give some inspiration for where to go to explore this in the future. So we could do the same thing with just a two-sided black hole, and we just evaporate one side. And this time we canonically purify the state, not on just one of the CFTs, but the union of both, so both on L and R. So canonically purifying before page time, we just get this. So again, we just introduce a second copy of this Cauchy slice and evolve forward and backward with reflecting boundary conditions. And now we have these two disconnected universes with entanglement between the bulk fields indicated with red. We can do the post-page time. Now we have a non-trivial QES, which is the union of chi-L and chi-R for the union of L and R on the boundary. And now we get this. So this time, instead earlier, we had that L connect to R tilde connect to L tilde. Now we get that L connects to its CPT conjugate L tilde, and R connects to R tilde. So somehow, if you compute this canonical purification square root of rho LR, which is a state on these four subsystems, as a function of time, suddenly we have a flip between what connects to what. So it could be interesting to study this state and look for patterns that can maybe help us understand connectivity. So let me summarize and speculate a little bit. So you show that the connectivity of the canonical purification of an evaporating black hole changes at the page time. A general procedure to implement ER equals CPR after page time exists, and we have given that procedure. Acting purely on the radiation before the page time cannot build a semi-classical ERB. So the story is slightly more subtle than you might think. And also diagnosing connectivity is really qualitatively different once we include a subleading 1 over n corrections. So some speculations, maybe multipartite measures of entanglement could tell us something. And they could maybe be interesting to study in this state here. Now, one thing speaking against that, that might just be my lack of creativity, but if you study such measures in just a normal two-sided case, so then you have to choose at least 3 subregions and kind of like, what is the natural 3 subregions to choose? That's not obvious. It seems like you have to kind of make some artificial divide, but maybe there is some good way to do it. How about the full spectrum, entanglement spectrum of the density matrix? So rather than just looking at the von Neumann entropy, maybe you can look at all the Rennies, or equivalently just looking at all these traces. So maybe like if you have that complete set of data or some subset of it, maybe that can tell you whether you're connected or not, because that contains, of course, a lot more info about the state. But the funny thing is that ER equals CPR cannot be true simultaneously with that proposal. So if you can diagnose connectivity from the spectrum, then ER equals CPR cannot be true in the way I've stated it. So let me remind you guys. So assume psi has an order 1 of Gn amount of entanglement between A and B, then there exists a factorized unitary UA times UB such that the final state has a connected semi-classical dual. That actually contradicts the statement that this list could diagnose connectivity, and the reason is the following. The spectrum cannot work if ER equals CPR is true, since if we can map the pre-page canonical purification to a connected spacetime with a factorized unitary, then we can map a disconnected spacetime to a connected spacetime without changing the spectrum. Because these factorized unitaries will not change the spectrum here. So if you believe proposal 2 is true, then this list of all the Rennies cannot tell whether we have connection or not. And okay, I think that's what I want to say. Thank you.
Any questions for Aasmund? Stop the recording so people can feel less constrained.